our first plenary talk, which will be by Davi Maximo. Dr. Maximo earned his PhD at the University of Texas at Austin in 2013, working with Dan Knopf. Since then, he has held positions at MSRI, Stanford, and the Institute for Advanced Study. He is currently an assistant professor at the University of Pennsylvania, where he continues his research in differential geometry, partial differential equations, and geometric topology. Today, he will be speaking about the waist inequality and positive scalar curvature. I think you may be muted.
Okay, yes, here we go. Thanks, Rose. Thank you so much for the introduction and also the invitation. I want to thank all the organizers. It would have been nice to see you last year, right? And you guys had to, figure it out how to postpone it and everything. So thanks again for putting this conference together. Okay, so today I'm going to talk about three manifolds with positive scalar curvature, and it's a topic that it's sort of the intersection of geometry, topology, and analysis. So I don't know if we're going to see a lot of algebra in the next hour, but you guys that are interested in algebra, please bear with me a little. So and the flow of the talk should be kind of laid back. So if you ever at any moment you want to ask a question, or if something is not clear enough, please just feel free to do so. Okay, so I want to start with the case of two dimensions, so that we get at least this sort of principle that are guiding this research in place. So when you're looking at things like curvature and topology and so on, I think that the sort of guiding principle is the uniformization theorem in dimension 2, because there in 2 dimensions we sort of understand how things are right, and then you kind of wonder what could be true also in 3 dimensions, in 4 dimensions, and it gets less and less clear, right? So to give an idea, we currently don't have like a program, at least a list of questions that if we were able to answer in sort of like a sequence in 4 dimensions, we would somehow have be able to say that we have understanding of how curvature and geometry are related in 4 dimensions. But okay, so let's start with dimension 2. So to get these principles in place, so suppose we have a closed surface with positive curvature. Okay, so we know by the uniformization theorem that it has to be a sphere. So as far as topological classification, right, there isn't much there. But if we somehow quantify how positive the curvature is, let's say if we assume that the curvature is bounded below by some positive constant kappa, then we can actually, there is these results, right, where we can bound the diameter from the surface from above, and also the area, again from above. And so in other words, having positive curvature in dimension 2, it's somehow allowing us to do a topological classification. But say a little more, actually, we are be able to talk say that the manifold is small. So I'm going to call that like geometric smallness. Okay. So those are the 2 sort of principles that I want to explore in 3 dimensions. So if I have now a 3 manifold with a certain curvature condition, right? Can I classify the topology first? And second, can I say that the manifold has to be small? Okay. I think that the natural curvature condition to look at first, right, at least, is the Ricci curvature, or maybe even sectional curvature. And in that case, both things are true. One is able to classify the topology. That's the result, for instance, by Hamilton from the 80s using Ricci flow. So it's so it's a difficult result, I would say. And but also you have this sort of geometric ideas like the Bonden-Myers theorem also works. You look at the variation theory of geodesics, which are curves that have the smallest length, right? And also volume comparison. You get that these manifolds must have, if you have a positive lower bound on the Ricci curvature, then you get that the diameter is bounded and also the volume is bounded from above. So here we do have that, and the sort of goal of this talk would be to talk about a recent result that I've done with Evgeny Lyubomovich from the University of Toronto that extend this to metrics of positive scalar curvature. Okay. All right. So first of all, then let's assume throughout the talk that we are in a closed manifold and the scalar curvature is bounded from below by a constant lambda, positive constant lambda. And let's somehow recall what scalar curvature is, by the way. So if you've never seen it, if you've never done a Riemannian geometry class and so on, basically the idea of these curvature quantities they go by like this. So you have your manifold and you want to be able to measure the lengths of curves, right? Distances and angles. So you need an inner product on it, right? So you basically put an inner product on every smooth chart and you assume that when you change charts, the inner product, changes in a natural way that is compatible. So that you have a smoothly varying inner product. And but it turns out that just from linear algebra, we know that at every point, right, at a manifold, if I look at the tangent space, I can always find the basis of the tangent space where that inner product, whatever it is, it looks diagonal, right? So that's just linear algebra. We are just doing it at a point. So but then the question remains, if we could do that locally, I mean, in the local neighborhood. So could I do could I find a neighborhood on my manifold that such that this inner product that was put in there somehow can be all diagonalizable? And it turns out that there are obstructions for that, and they come from curvature. So basically, this curvature, comes from somehow. This is the sort of best you can do if you choose a point on your manifold. You can diagonalize the inner product at the point. So if you see like x, if x are 0, so here you have the delta ij, which is the identity matrix. But as soon as you start moving, to points nearby, you have this obstruction here of second order. So amazingly, you can make the variation 0 of first order. So you see that this is a Taylor expansion. There is no first order term, but then there is the second order term here, which is this guy. And this is where this shown that this is an invariant of this inner product that he put there, which we call the Riemann curvature. Okay. And as you can see, it's something that, what is these RJKL? Well, this is basically, it's a monster for linear algebra, right? You have to, this is like a 4 tensor, okay? And it's kind of hard to, to kind of get a handle of it, especially put a sign. What does it mean to have positive curvature? I mean, do you assume that all these guys are positive, So the sort of right notion of positive curvature, it might be a little elusive, but one that the scalar curvature, at least the one that you were going to be interested in, comes when you calculate the volume. So for example, if I take a very small ball at a point and I calculate the volume of a ball of radius epsilon, say using the delta in the product, that's just the Euclidean, a volume. And then I also calculate with the volume with this metric G, and I compare the two. I do the ratio, and it turns out that ratio looks like this in epsilon, at least asymptotically. So this number here, Rp, right? R at the point P, which is the center of this ball. This is what the scalar curvature is. Okay, so it's basically you put in the product on your manifold, and then you know that x 0th order you are Euclidean, right? But when you start looking at now higher order variations, you have this sort of like Taylor expansion for the volume. And so basically having a metric of positive scalar curvature is telling you that locally, at least, right, infinitesimally, you have less volume than the Euclidean, metric. Okay, so it sounds very flexible, especially if you think that volume. I mean, it's a quantity that it's somehow, flexible. If you just have, so it seems that, positive scalar curvature might be kind of weak condition, right? And let me actually tell you in the next slide why, a few more facts that, highlight how weak positive scalar curvature is in some sense, okay? But I should say, if you've never taken a Riemannian geometry class, this definition that I just gave you is not the one that you're going to see there. It has actually never been used to prove anything about scalar curvature, but I just think it's cute. Okay, so let's see that scalar curvature is weak. Okay. All right, so the first sort of result pointing to that direction is this result that if you give me any function on the manifold that is negative at some point, I just ask, can be anything, just let it be negative somewhere, you choose the point, right? Then it turns out that that function is the scalar curvature of some metric, right? So you can prescribe the scalar curvature. So that's kind of an amazing result to think about geometrically, and it turns out that the proof is it's basically PDEs. But another fact that shows that how weak it is in some sense, how flexible it is that any manifold with boundary, you can put a metric of positive scalar curvature there. And you can actually prove this. You can actually prove this second point by using the first. If you think about it, you just take your manifold in boundary and you double the boundary, right? And then you just choose a function f that is negative in one of the halves of the double, so that when you restrict to the original manifold in boundary, it's going to be a positive function everywhere, right? So very flexible. So there is no topological obstruction or anything for manifolds with boundary. The other one, which it started to get a little, it might not be that interesting topologically, but I think geometrically is very interesting, is this question that is the thing that if you take a manifold, so I just had a question about what the hypotheses. I think if you just take for M on the first point that you prescribe, if M is closed, that's a true, any closed manifold you can, as long as a function is negative somewhere, you can prescribe, okay? But if you want to make it everywhere positive, then it turns out that there is an obstruction, which is the amazing thing. Okay, so back to M cross S2. So if you choose any manifold with a metric, so this manifold M can be very ugly, a closed manifold, right? Ugly as far as positive curvature goes. It can be very complicated, have fingers sticking out, right? So something that the geometry just look like a mess, right? But as you just give me that, and I just take a small S2, I just make it very small. Small S2 has very large curvature, right? So I cross that with S2. This new guy will have positive scalar curvature, it turns out. So so you can make very strange looking manifolds this way. And the next one is it's something that the topologists like, that you can do connected sums. So it's flat. So scalar curvature. If you give me any, this is true. I just made this drawing in 2 dimensions, but if you do that in higher dimensions, you can actually do surgeries if you want, and keep this property of having the metric of positive scalar curvature. So if you have 2 manifolds that emit a metric of positive scalar curvature, you can do a connected sum of them. This is a process called Gromov-Lossov construction, and so it basically, this is very drastically different from Ricci curvature, let's say, or sectional curvature even, where you have you have much tougher restrictions. Okay, so if you try to think then about geometric smallness, this slide here starts to look like an issue for you, because if you have two manifold, if you have a manifold that has positive scalar curvature, you can start doing connected sums with itself, right? So in particular, you can start making produce manifolds that have the same lower bound on scalar curvature as you originally did, but the diameter is getting bigger, right? And also the volume is getting bigger. Okay, but this is actually something. This is important for this geometric smallness that we are seeking. Okay. Now, on the other hand, it turns out that if you look at the literature, you also see that scalar curvature is strong. Okay, so it turns out that there are obstructions. So over the years, people have actually found invariants for a manifold to admit a metrical positive scalar curvature. So, which is amazing. So if you compare with the previous slide where I said you can prescribe any function as a scalar curvature as long as it is negative at some point, just a tiny bit in a tiny ball is enough, right? But you cannot make it positive everywhere in some manifolds. So this is something that you actually have an invariant when your manifold spin. It's called the heterogeneous. But if your manifold is not a spin manifold, then there's some other techniques based on the medieval hypersurfaces. So it's strong in that sense. And also, if you look at the field that sort of Riemannian geometry comes from, right, which is general relativity, the scalar curvature plays a huge role there because it's the Lagrangian density for this Einstein-Hilbert action. Okay, so it really plays a role. So having a positive scalar curvature is almost like having like a positive mass density, right? So it's very prominent in general relativity. And in fact, it seems that on the previous slide I was saying that it's weak, but at least in 3 dimensions we actually have a topological classification. So it's strong enough that for 3 manifolds, if you compare the work of Shen and Yao and Perelman, we know that a manifold that emits a metric of positive scalar curvature if and only if it looks like connected sum like this, a sphere and then connected sum, a bunch of spherical space forms, these S3 mod gammas, and also some S2 cross S1s. So you see the round metric on the sphere has positive scalar curvature. So this guy has a metrical positive scalar curvature, and so does these quotients, and so does S2 cross S1. So all of these individually, they have a metrical positive scalar curvature. And because you have the Gromov-Lossov construction, in other words, you can take connected sums of things with positive scalar curvature, you see that there are metrics of positive scalar curvature for any of these examples. So it's in a way is a complete picture, right? So if you have a metric of positive scalar curvature, you must look like this. But also, if you look like this, you admit a metric of positive scalar curvature. Okay, so it's a very satisfying picture. Okay, so let me say a few things about how this is done, right? Because again, so this work of Shen, Yao, and Perelman, it predates our work by 20 years. So, and somehow was the motivation for us to start, because when we start thinking about this, we knew that the topology was understood, right? Now, the real thing to understand was the geometric smallness. Somehow, it doesn't even make sense to say. And I say geometric smallness here because instead of saying that bounded diameter or bounded the area, because those are not true. There, as you can see by the connected sum, you cannot bound the diameter of such manifolds. You cannot bound the volume either. Okay, so we have to find the proper sense in which they're small. Okay, so let me say a few words about how at least the topological classification is attained. Okay, and it turns out that it started back in the 70s when Shen and Yao made this basic but fundamental observation, which was that any closed surface that minimizes area, okay, up to second order. So in other words, it minimizes area at least like for like as far as like the second order perturbations are concerned. On a 3 manifold of positive scalar curvature, those surfaces must be 2 spheres topologically. Okay, so you see, if you're not from the field of geometry, and you might wonder about this, so Riemannian geometry had huge developments in the 30s, 40s, and 50s by studying the distance function. So in other words, people were looking at geodesics, curves that minimize the length. And this is typically the first thing we learn when we take a course in Riemannian geometry. But what Shen Yao did was that they started, instead of looking at curves, right? They started looking at surfaces that minimize, now instead of minimizing the length, they minimize the area. And it turns out that these surfaces, the methods become more powerful. So they were able to do this because the theory, the analytic theory for these surfaces was kind of put in a good ground in the 1960s. So then in the 70s was, the ground was laid for people to start using these methods. Okay. So it's a sort of how is a natural extension. If you study, if you've seen like studies of Ricci curvature, like the Bond-Myers theorem, where you have a positive bound on Ricci curvature, then you can bound the diameter from above. That's basically by looking at a geodesic, right? So for scalar curvature, geodesics, they're too weak, they have codimension too. So, but it turns out that if you look at surfaces, you have information. But okay, this fact, how do you put it together to actually classify things? So it turns out that, okay, they made this observation, and then they also realized a minimization scheme for incompressible surfaces. So if I have an incompressible surface on my manifold, I can start minimizing area, okay? And they proved that this will converge to an area minimizing surface, okay? So using that, and then the fact that, okay, so if I have a compressible surface and I start minimizing the area, I get a stable surface. But if I'm on a manifold of positive scalar curvature, these surfaces must be spheres, okay? So what, if you put 1 and 2 together here, these 2 points, you actually get that you understand then the fundamental group of these manifolds, right? So they understood the fundamental group of manifolds of positive scalar curvature this way. And then, finally, Perelman came around, and he realized the geometrization conjecture, and from there we can understand now 3 manifolds through the fundamental group. Okay, so let me just show a picture. For example, in the case of the 3 torus, which was the manifold that was open, in the 70s, people didn't know whether the 3 torus admitted a metric of positive scalar curvature or not. So, and Shen and Yao, they proved that it doesn't. So basically, if I have the 3 torus, I start here with an incompressible 2 torus in this blue guy, and I start minimizing area. Okay, I start, and this is where the analysis come in. You have to show that this process, if you start minimizing area, amongst all surfaces that have the same action in the fundamental group, you end up with this red surface here, which is a smooth. It's going to be what we call the minimal surface that is stable. But then by that observation, if something like this exists on the manifold, it should be a sphere. A torus cannot appear as a stable minimal surfaces under positive scalar curvature. So, and I'll go back to that in a future slides and actually show you why that's the case. Okay, so any questions so far? So maybe it's a good time to start talking about the geometric smallness. So, okay, so we now know the topology of these manifolds. And sorry for you folks that work in hyperbolic manifolds that they don't show up, right? In that, otherwise it will be too hard, right? But it's somehow we now know that what they look like, right? And they don't have to be small. So for example, I can have something like this, which here, this is not a surface of genus 8, by the way. This is just, you just take your favorite manifolds with positive scalar curvature and you start doing connected sums, and and you go about your life, and it can start getting very complicated, right? kind of like, following a graph, okay, if you will. So it turns out that, modulo this codimension 2 data, you really don't have a hope to show that they're small, right? They have this one-dimensional freedom, if you will, almost, right? Because you can start like expanding them, like following a graph, okay? So, and it turns out that if you put this together with that, what I said earlier, that if you give me any manifold, when anything, you can just cross that with S2, and that would have a metrical positive scalar curvature. That's again another evidence that, the best you can do really maybe is something modulo codimension 2, right? So it turns out that there is a conjecture of Gromov about that, which is that if you have a manifold with positive scalar curvature, then there should exist a polyhedral complex of codimension 2 and a map from your manifold to it, such that the preimages of every point in the polyhedron have bounded diameter and bounded area. So these are universal constants, right? So in other words, it only depends on the lower bound on the scalar curvature. Remember, this lambda is the lower bound we have on the scalar curvature, okay? So for us, this what geometric small is somehow what we can hope for, showing that these guys are small. So it's modulo a codimension 2 object, they are small, okay? And again, by the examples, by the constructions, you see that this is the best you can do, because you can take, for instance, you can take your favorite tree, right? You take a one-dimensional tree, a graph, and you start with put spheres on the vertices, and then you start gluing them, okay? And that way you get an example of a manifold with positive scalar curvature, okay? And this is what we will prove, guys. So so we prove that for any manifold, three manifold, right, with a metric positive scalar curvature, there exists a metric graph gamma and these functions f from m to gamma, such that the preimage of every point, it has bounded area, bounded diameter. This is the extrinsic diameter, by the way. And we are also able to bound the genus. In this case, these are going to be topological surfaces, right? So most of the time they're going to be smooth, but even if when they're not, we get a genus bound, which is at most 6. Okay. Now, whenever you give this talk to analysts, they always ask, "Oh, are these sharp? Are these the best constants you can put there, and so on?" And the answer is not in general. If you know that the manifold M is the sphere, the 3-sphere, right? This is a still interesting question, because you see topologically the sphere is simple, but geometrically it can have fingers, like a 3-sphere can still look like geometrically complicated. And in that case we have a sharp result, but not in general. We also have a theorem B, where somehow we can rewrite this by, instead of looking at a graph, we say that there exists a Morse function H, okay, such that the preimage of every point under this Morse function, the connected components are gonna be geometrically small. Okay, so we cannot bound every level set, because the level set might be disconnected. Okay, but and then when you add that up, it can be big. And in fact, there are examples of manifolds like that, where there is no Morse function where every level set is small. I mean, it's controlled. But we prove that at least the connected components, they have to be small. Okay. So what I'll do today, folks, is I'll talk about theorem A. The proof of theorem B, it comes from theorem A by just like doing some cutting and pasting and and constructing this Morse function basically by hand. Okay, I think that the real geometric issues are in proving theorem A. So I'll focus on that. Okay, any questions about the geometric smallness or what we're gonna seek to do? Okay, so if not, let me get going. So really, the starting point for us, right, was okay. So what can you control with scalar curvature? And it turns out that what was known that we can control scalar curvature, right, on the three manifold geometrically, and we only knew that a couple things, that scalar curvature, a lower bound on scalar curvature gives you control on certain kinds of minimal surfaces, right? So before I already said topological control, but there is actually a geometric component to that control. So we can actually control the diameter and the area of certain kinds of minimal surfaces. Okay, which they are the minimal surfaces that we call of index 0 or 1. So the point will be to start from those and then somehow try to propagate those bounds through the regions. Okay, so let me state at least the strategy. So, okay, this is a picture of what the theorem looks like. So if for any manifold there exists this graph, and then the pre-image, it's going to be this connected thing that in this case is a sphere, but it could be up to genus 6, and it's going to have bounded area and bounded diameter. Okay. All right. So what is the strategy would be to first start from this point that a lower bound on scalar curvature gives us geometric control over certain kinds of minimal surfaces. Okay, in other words, surfaces that minimize the area in some sense. And then we're going to cut the manifold along those surfaces. We're going to get a manifold with manifolds with boundary. And then we're going to start propagating those bounds by using flows, a geometric flow, which is called mean curvature flow, and some metric geometry ideas. So we want to control both area and diameter. And it turns out that there isn't a single one way that you can do both at a time. So you have one procedure to foliate things, controlling the area, and you have another one by foliating things, controlling the diameter. So we kind of have to play with both. Okay. And this process of doing this foliation by these pieces, basically, when you look at closely, it's constructing you the graph. Okay, the map, the graph gamma, and also the map. So really what we are doing is we want to show the existence of a certain kind of foliation, like a singular type of foliation that has all the leaves have controlled area and controlled diameter. Okay. Okay, so let me tell you a point about this first remark here, which is that positive scalar curvature gives you geometric control over certain kinds of surfaces that minimize area in some sense, right? So that sounds very vague, but let me tell you what I mean in a second. So when you have a surface on your manifold, let's say a surface sigma, right? And you want to look at the variations of area, a typical thing to do is to look at just like is to do the second derivative test of calculus, right? You take a variation of the surface, which is just like, you pick a function on your manifold and you deform your surface along the direction of that function times the normal. So, and you calculate the area of that, and you take two derivatives at t equals 0, which is your original surface, and then you get this expression. Okay, so if you ever seen this done for the length functional, it's very similar. You get one derivative of the variation, and then you get over there you get the Ricci curvature term. Well, you get a curvature term, but in the surface case you get this Ricci curvature term where n is the normal of the. Let's see here. Where can I get the drawing tool? Oops. I'm trying to see, folks, where can I draw here? Let's see. So more pause recording shows a traffic script. Interesting. I'm looking for the little pen that allows me to draw things with the mouse, but I can't find it. Remote control. I don't think that's it. You would think that one by now, right? Would have figured out Zoom, but not quite. Okay, so this is the second variation, and where does the scalar curvature of the ambient where the surface live is influencing this surface? Okay, so the idea is that whenever you are, say, stable, which means that you are area minimizing up to second order, what that means is that for any function phi that I take, okay, and I do this perturbation, this second derivative is greater or equal than 0, right? So in other words, the area cannot decrease up to second order. So that tells me that this operator here, L, which is Laplacian plus Ricci plus a squared, this has a non-negative first eigenvalue. Okay. So and what do we do with this? Well, the connection of scalar curvature is here. When the scalar curvature of your manifold is positive, then when I look at this metric, U squared times G restricted to sigma. So what is this? I have my surface on my manifold and I have this smoothly varying inner product on the manifold. Well, I can restrict that inner product to the surface, which is this G restricted to sigma. What is that? That's just a way of calculating the size of tangent vectors on the surface, right? So, okay, so I have that. So that's an inner product on the surface alone. And but then I also have this function U on the surface, which comes from the fact that that surface, it minimizes the area, up to second order. Okay, so so that's the connection. So if I take that function, which is a positive function, so if I do that U squared times G, so this is still unadmissible in the product. You see, if G is a non-degenerate, right, in the product, smoothly variant, then a positive function squared times that is still going to be an admissible in the product. And it turns out that this new metric, so it's a new in the product, this gives us a metric of positive Gauss curvature on the surface. Okay, so in particular, that surface has to be a sphere, because if it admits a metric of positive Gauss curvature, then it has to be a sphere by Gauss-Bonnet. Okay, so it's not that if you have positive scalar curvature on a three manifold and you have a surface in there and you restrict the metric, then that metric, it's going to have positive scalar curvature all along the surface as a manifold on its own. Not quite that, but there is a deformation that comes from the problem of area that minimize, the problem of minimizing area, that if you change that in the product by that deformation, then you do get a metric with positive Gauss curvature. And it turns out that this works in a way that if I had a lower bound for the scalar curvature on the three manifold, then I would get a lower bound on the Gauss curvature of this metric U. So that's why these guys, they do have geometric smallness, because a positive lower bound on scalar curvature also translates to a positive lower bound here. Now, if you actually want to prove this, which is the statement of this next theorem, you have to work a little more, because you have to control that function U squared, right? Because in the end, we want to say something about the original inner product G, not U squared G. Okay, so there is some details to be worked out there, but that's where the connection comes from. And what it allows you to do is allows you to say that if you have a manifold with positive scalar curvature, strictly positive, then if I have a minimal surface on it, and if that minimal surface is stable, that's when you minimize area up to up to second order, right? You can do that trick. Then you can bound so there are two cases. One is the case with boundary and the one is the closed case. So if you have boundary, then you can bound the distance from a point on your surface to the boundary. So that's at most 2 pi over root lambda. But if you're closed, then you can bound the diameter, okay? And now for C, if you have a surface of index 1, so what is a surface of index 1? Well, it's the next, sometimes when you try to minimize area, right? For example, on the three-sphere, the round three-sphere, if I try to find, if I take a two-sphere inside the three-sphere, the round two-sphere, and I start minimizing area, well, I just shrink to a point, right? So in that case, you cannot really minimize area all the way. So an index 1 surface is basically, it's just, it comes from Morse theory, really, right? This whole nomenclature. It's basically, it's a surface that minimizes area, except for one direction, So let's put it this way. So, and it turns out that you can still control geometrically those surfaces as well, okay? So you get the bound on the diameter from above. It's a worse bound, but it's just because you have less control over the surface, right? And similarly, you can also prove that you can bound the area of these surfaces from above. Okay, so the area is at most 8 pi over lambda in the case of stable, and in the case of index 1, it's at most 32 pi over lambda. So, okay. So then this is precisely what I was saying, that, this is the starting point for us, because we know that if I have positive scalar curvature, the only geometric smallness that I can prove on the manifold is the geometric smallness of these minimal surfaces of index 0 and 1. Now the question is, how do I propagate these bounds like that from those surfaces to the whole manifold and get a foliation, okay? So what I will do is we'll cut this, we'll cut this manifold. We have to prove that these exist, right? So we have, and we want to cut along those surfaces. So we have this result, and we have this technical term here we call geometrically prime region, which is basically, this is a manifold with boundary, right? Where all the boundary are stable to spheres, except for one boundary component, which it's either a minimal surface of index 1 or something mean convex. And I'll say what mean convex is in a second. And in the interior of that, there are no closed embedded minimal surfaces. Okay, so it's what you would expect if you had your manifold and you cut along this index 0 and index 1 minimal surfaces, the most you could. All right, so we proved that if you have a manifold with a metric of positive scalar curvature, then you can, there is a finite family of these surfaces. All of them have genus at most 2, and that the disjoint union is what are these geometrically prime regions. Okay, so let me say a word about this decomposition theorem, maybe in the next slide where I have a picture. So, and again, I should say here what I mean by the word bumpy. Okay, but it's just a minor technical assumption. So basically, if I have a manifold and I want to cut it along stable minimal spheres, one worry that I should get is that if I have like a piece of a cylinder, so imagine if I have like a piece of a round cylinder. So in a round cylinder, every slice is going to be a stable minimal surface, right? So where do I cut? I have infinitely many choices there. So bumpiness, right? It's a generic condition. So in other words, I can approximate any metric by a bumpy metric as close as I want. And what bumpiness does for you is, it's kind of, the word suggests, it introduces bumps on the metric that make sure that you don't have a one parameter family of these minimal surfaces. Because if you had a one parameter family of minimal surfaces like that, of a stable minimal surface index 1, you wouldn't be able to decompose this, right? You would cut and there would still be one immediately close. So that's what bumpiness means, okay? And the important thing for us is that we can assume bumpiness because our result is, we want to prove that decomposition, and we just prove for a bumpy metric nearby, okay? And then the result is true then for any metric. Okay, so suppose if I have a bumpy metric, like on, for example, this is a 3-sphere with a sort of strange looking metric, which is bumpy, so no pieces of cylinders. So what I'll do is I first choose a maximal family of disjoint stable true spheres. So these exist, for example, if our manifold has a non-trivial pi2, you can take a non-trivial homotopy class in pi2 on your manifold, and you can minimize the area there, right? And then you can find a stable true sphere. That's what, involves some analysis, but you can do that. So that, so depending on the manifold that you have, like for example, if you did a lot of connected sums when you build this manifold, right? So those connected sums, they come with a stable minimal true sphere there. Okay, so you first look at the maximal collection of disjoint true spheres like this. Then I'm going to look at the complement of these. These are going to be manifolds with a boundary, but the boundaries are true spheres, and they are stable true spheres. So it turns out this uses the topological classification that all these manifolds here with boundary, they have to be basically handle bodies, right, with these balls removed. And in the handle bodies, if I choose a Hagar splitting, it actually, again, by the topological classification, it has a Hagar splitting, a reducible Hagar splitting of genus at most 2. So it could be 0, 1, or 2, but it's at most 2. So I'm going to choose the Hagar splitting, right? And then I'm going to use this other analytical theory, which is called the Mimax theory, that tells me that I can isotope irreducible Hagar splitting to something that minimizes area up to one direction. So index 1 minimal surface. Okay, and then in the end, I have a picture like this. So you see, if I then cut, along these, right, red and blue surfaces, whatever I have left, it's what I call a geometrical prime region. So in other words, it's a region where I have one large component, which is the blue guy, right? And then I have these spheres of smaller area. And basically the theorem is done if I can prove that if I can show that it's true for geometrically prime regions. So if I can foliate this, right, starting from this, for example, if I take this guy and I foliate it, started from the big one, from the blue one, I can foliate it to this other pieces. I get the result for this piece, but then I can also get for this one, and all the pieces, I just put it together, and that gives me the graph. All right. Okay, so so let me just tell you an idea of, give you an idea of how you propagate those bounds, and then I think at least the area bounds. Sort of what are the tools that you use to do that. So for the area bounds, the tools is to use mean curvature flow. So mean curvature flow, it's basically a flow that, when you do the first variation of area, you have this thing called the mean curvature vector, which is basically of a surface. It's basically a direction that is telling you where you should move to decrease the area the fastest as possible, right? And when I have a surface like this, well, a minimal surface has mean curvature 0. You cannot reduce the area up to first order, right? But if I have a stable surface like this one here, which has index 1, so I know that there is one direction that I decrease the area. So if I push it that direction, I will get a surface that is mean convex. And then once it's mean convex, I can start pushing in the mean convex direction. This is what we call mean curvature flow. So you're flowing by mean curvature. You are letting the mean curvature tell you at each point where you should go. And a good thing about the mean convex flow, like mean convex, mean curvature flow, is that it's monotone. You see, like it preserves mean convexity. So whatever region the mean curvature flow points, right? I start flowing, and it's always going to flow inside. So this is what the flow will do. It's going to flow, but the problem is that it will have to be, it starts flowing and flowing, right? But okay, this flow can get singularities in the sense that you can start to have a neck, and then the curvature gets so tiny that the neck pops, right? So this will actually happen here in this case, right? Because if I have one boundary component, large boundary component like this S1, and I have the other small spheres, this should flow all the way to S2, S3, S4. Now, I had an area bound for the blue surface, but because this is a mean convex flow, the area is always decreasing. So the area bound, it's also true for the red surfaces, okay? So that's how you propagate the area bounds. But we have a problem with surgeries, which, with surgeries, because, what happens is that I could start flowing maybe a sphere like this, and then the curvature gets super large, like at this point, okay? So basically what we have to do is that we have to come and cut this and glue in caps here so that we can continue. So this will flow inside here, this will flow here. And this part is so small, it's kind of that, it gets discarded by the flow process. So that's one of the tools. So for us, because we want to find a foliation of the manifold of geometric control, the thing that makes mean curvature flow work for us is that the potentially bad regions, which are these regions where I have surgery, I have geometric control. I know that they're small. So I already have geometric smallness in some sense, right? So I can handle them by hand, okay? But to do, to now get the, this is sort of the blurb about like the technical assumptions of the mean curvature flow. Let me spare you of that. But to get now the diameter bounds, what we do is we use some metric geometry, and we start looking at the equidistant surface. So basically, we prove this lemma, which is just a stepping lemma to prove this important lemma here, which says that if a connected surface is contained between two equidistant surfaces, sigma x plus rho, where rho is 10 pi over lambda, then I can bound the diameter. So in other words, I have here my S1, I start flowing by mean curvature, and mean curvature preserves the area bound, but might destroy the diameter bound. The diameter might increase, right? So that's a problem. So if the diameter starts to get too big, so in other words, I look at the point here that is closest to the original surface and the point that is furthest to the original surface. So this guy here is this guy, and they are like 10 pi over root lambda apart, right? So pretty far apart. Well, basically what I do is I stop the flow, and then I cut by the equidistant surface, which is the midpoint. So I cut by this sigma L, where L is like rho over 2. And then I glue in minimal surfaces here, this green guy, and I start flowing again, okay? So that way, these new flows, right, will still be trapped between the sigma s and sigma s plus rho. So I'll still have this bound 40 pi over root lambda, at least for a short time. And if you think about it, guys, this process is precisely the process where the graph, that's the reason why I get a graph in order foliation, because you see, I had one surface flowing, but then there was a point in time where I split in two, right? So I had to split into this one, and I had to split into this other one. So that's why, you get this sort of, it's not a foliation, right? Because the parameter is sort of splitting. The parameters, they're not very overitable. They're varying over a one-dimensional graph, okay? But these are the sort of tools that you use. There's a little bit of analysis that, we swept under the rug, but I guess that's fine. So thanks for your attention, okay?
Thank you, speaker. Are there any questions? Please feel free to unmute if you would be comfortable with that, or to ask in the chat.
I guess it was a super clear talk, no?
All right, let's thank the speaker
Well,
again.
hold on. I guess, Davi,
Yes.
to sort of like, you know, make sure I understood like the whole thing you talked about at the beginning is, you know, this is like supposed to be a paradigm for classification of three manifolds, and the way you do that is sort of by mapping to these graphs and sort of knowing that, you know, in some sense,
Yeah.
if two manifolds can map to the same sort of graph, then they must be, you know, similar in some way.
Yeah, well, so we have the topological classification by the work of Shen Yao and Perelman, right? So we know what they look like, the topology, what it is. So when we understand fundamental group, I mean, we understand the diffeomorphism class. So what we were looking to do was to prove it was seeking to understand what does geometric smallness means in the case of positive scalar curvature. And this project was, so I started with this thing about scalar curvature is weak, scalar curvature is strong. And it's precisely because, you know, scalar curvature is this interesting curvature condition where you don't know what's going to be true, right? It's malleable, right? So there are some results where that you can sort of, that you would expect for you know, classical curvatures like a sectional curvature where, you know, it's a very strong yield on your to have a sign, right, on sectional curvature for a manifold. So okay, you cannot hope to classify that, you know, like for example, we don't know the classification of 4 manifolds with positive sectional curvature, so let alone scalar curvature, right? So it's sort of this curvature condition that it's intermediate, right? It's almost it's so the one thing for us was to, I mean, when we found this conjecture of Gromov, it really inspired us because we okay, this is what should be true, right? So, you know, I imagine people try to bound the diameter, right, like or the area before maybe the Gromov loss of conjecture was the Gromov loss of construction was done, but it's it was really about like to show how small they're going to be, right? And I think that this is a principle that is still not very well understood to at least the manifestations in higher dimensions, right? Which should be that a manifold with positive scalar curvature should be small up to dimension 2. So there is these like codimension 2 conjectures, right, where things are nice, you know, except for a codimension 2, you know, a codimension 2 maybe object. So the point was for us, the missing piece was this geometric smallness.
Thank you.
All right, let's thank him again.
Thank you for the question. Okay, thank you.
Our next session is going to be a coffee break. I will put the link to the Gather Town in the chat for everyone if you would like to join that for some smaller discussions. Thank you, everyone.
Thank you. Let's see.
So I have a quick question about joining the 30-minute talk. So what link should I follow?